In this episode, I'll show you the project we did at the Asian Institute of Management for my master's degree for the subject Machine Learning 2, where we use machine learning to detect atrial fibrillation using ECG signal. Shout out to my teammates Gavin Kua, Ron Lau, and Ali Valerio for helping out in this project. So let's begin. Meet Uncle John and Auntie Anne. They are the prime of their life and have been married for the last 50 years. While enjoying each other's companion, one thing they are worried about is their health. At their age, health is of primary importance. One of the major concerns of elderly people is what we call atrial fibrillation. Atrial fibrillation is a type of arrhythmia which can be life-threatening. Arrhythmia is basically an irregular heartbeat. Either the heart beats too fast or too slow, where people would feel like a pounding or racing heartbeat. And most of the arrhythmia are harmless. Atrial fibrillation is one that can be life-threatening. It is a primary cause of stroke and heart failure, and the good news is with early detection of AFib or atrial fibrillation, one can reduce the health risk with proper intervention. Atrial fibrillation is a growing health concern. Globally, there's about 37 million people who have recorded with this case. In the Philippines, there's about 200,000, and a lot of these people are the elderlies who are 70 years older and above. The main problem in our country is that there is a lack of monitoring of atrial fibrillation. In Philippines, atrial fibrillation presents significant health because while management and care is available, there are gaps with regards to screening and diagnosis of atrial fibrillation. So what we present is a cost-effective solution using smartwatches with PPG or single short ECG to be able to detect atrial fibrillation in real time. So this is how we develop the machine learning model. We use an existing dataset from MIT Beth Israel Hospital, which is an arrhythmia database. This contains 500 records with a proper distribution of different types of beats, from normal to supraventricular, ventricular, fusion beats, and unknown beats. So the dataset is balanced, and these are the different types of signals. In here, you will see the different ECG signals of different types of beats, starting off with normal beats. And if we compare the normal beats with supraventricular beats, the main difference is essentially on the distance between the peaks. So if you notice, the normal peaks have equal distribution across all the signals, while supraventricular will have longer or sometimes shorter distance between the peaks. For ventricular, you'll see certain irregularities, and for the fusion, essentially a combination of the different waves, the pattern is a bit abnormal. For unknown, they are harder to classify. For this project, we are more specifically interested in atrial fibrillation because that is one that has been identified as more harmful. So we start off by detecting peak-to-peak detection. That is identifying each peak and computing the distance between each peak. However, running the signal processing directly from the data did not work properly. We are not able to get good response. As you'll notice from the graph down here, the algorithm is not able to detect all the peaks. There are certain peaks that are detected, but some are being skipped, similar to the signal on the right-hand side. So we had to look into other ways on how to accurately detect the peaks, and we tried using Pan-Tompkins. Pan-Tompkins is a widely used signal to detect ECG signals, which is composed of multi-step process. First is the noise filtering, then followed by derivative calculation, squaring function, moving window, and threshold. I'll explain all of this in the next few slides. Starting off with this kind of signal, the first step that we want to do is noise filtering. The signal is now cleaner, where we remove certain noise. Once that's done, we then compute for the derivative. When we compute for a derivative of the signal, essentially we are amplifying the slope of the signal because we are more interested in the changes of the signal. So computing the derivative amplifies the changes in the signal, and then we perform a square so that we remove all the negative values and exponentially increase the amplitude of each signal. So this is the squared signal. We then perform a moving window so that we smoothen all the peaks and come up with this signal. From the moving window, we then perform a peak detection, and this time we are able to get a more accurate detection. But take note that we are not only using the QRS signal. After reviewing how cardiologists actually read the ECG signal, we notice that there's PQRST. We are not only interested in R, but we also wanted to check the other parts of the signal, which are PQ, S, and T. So, using the same algorithm, we are then able to get the PQRST of each signal. From here, we perform feature extraction and correlation analysis. So, using the PQRST signal, we then come up with different features such as the peak-to-peak mean, the standard deviation, the square difference, and as well as the QRS features and the heart rate and the power and signal analysis. So using all these features, we have then performed hyperparameter tuning. We tried different machine learning methods using Bayesian optimization to find the most accurate detection, and it turns out that random forest has the highest accuracy, resulting to 99.75% on training data and 96% on test data. You can also see the F1 and sensitivity and specificity score in this chart. Note that Odell also perfectly detected normal signals. So anything that is not normal will probably fall within one of the classifications below. But we do not stop there. We want to be able to interpret what this actually means. We're able to find out using interpretability tools that QRS duration and PQ interval are the most important features to detect atrial fibrillation. So essentially, we are looking at the duration of the signal, which we have identified earlier, right? For normal, you'll have an equal distribution, and for supraventricular or atrial fibrillation, the distance is farther apart. You'll notice also that for ventricular, where the signal is a bit abnormal, we also identify the signal entropy as a major feature affecting the performance. For fusion, these are some of the features that has been identified as important. And for QR interval, there's not a lot of features that are found important, primarily because there's no pattern in their signal. So with this, we're able to show that using proper signal processing and machine learning, we'll be able to use cheaper devices to screen for atrial fibrillation, which can help people like Uncle John and Auntie Ann enjoy their life by taking care of their health and be able to screen themselves against atrial fibrillation using just smartwatches. With that, I hope you enjoyed our presentation. Please click like and subscribe if you want to learn more about AI. And this is another episode of Artificially Intelligent.